All right, so we're off to chapter 9, which is chemical quantities. And chapter 9 kind of puts together a couple of things of the last two chapters that we've been talking about. It puts together the molar mass conversion, which is our grams per mole. And remember, that is we get from the periodic table. That is what we use to go from grams to moles. And moles back to grams is, again, from the periodic table, the bottom on the bottom there. And also balancing equations. And kind of putting these together is what is known as stoichiometry. And what that allows you to do is, from a balanced equation, you could calculate things like, if you know how much reactants you start with, you can figure out how much products you would make. Or if you know how much products you made, you could go back, calculate, and figure out how much reactants you started with. You could also, as we'll talk about, figure out if you have one reactant, how much of the other one you would need to react with it. And also product-wise as well, if you figure out how much of one product you produce, you could also figure out how much of the other product you produce. So it really does sort of tie together these two ideas in this chapter. So let's get into it here. So when we do have a balanced equation, there's a couple of ways we could look at a balanced equation to help us out. We could look at these coefficients here, the two, basically the 1 and the 2, as being two molecules of H2 react with one molecule of O2 to give you two molecules of H2O. We could also look at it, which is primarily what we're going to use in this chapter, which is sometimes referred to as the mole-to-mole relationship. And those coefficients can represent the moles of each of those things. So we could say there's 2 moles of H2 reacts with 1 mole of O2 and 2 moles of H2O. So really in this chapter, that's probably the one we're going to use the most in terms of that relationship. And sometimes people get really confused about kind of like where you get those numbers from. So it is just literally that it comes from the balanced equation. It's those coefficients. So that is where we get those numbers from. The bottom here is the conservation of mass. So if we have 36 grams of reactants, we also have 36 grams of products. We know that from what we talked about balancing equations. So if we started with 4 carbons on the left, we will also end with 4 carbons on the right. And since the mass of the carbon on the left and right-hand side of the arrow is still 12, you should have the same mass of reactants and products basically that's going on. So the amounts of reactants and products is what I had mentioned before is what's known as stoichiometry, and people get freaked out by that word, but really, as we'll talk about, it is really just a conversion that you use the equation to get. And like I mentioned a second ago, you really can solve for any of those things. You can, if you have an equation, for example, one like this, you could figure out if you just knew anything about A, you could figure out how much B you would need, how much C you would produce, how much D you would produce. Also, if you know how much D you produce, you can figure out how much C you would produce, how much B you started with, and how much A you started with. Again, you can do these relationships as we'll see. You don't have to cross over the arrow, so you could do these relationships between two reactants. You could do this sort of relationship between two products as well. So sometimes people think you have to do a stoichiometry relationship and cross over the arrow from one side to the next, but you don't have to. You can stay on the same side, or you can cross over the side. But it does allow us that if all you know is the equation and you just know really one piece of information, how much either you started with or how much you produced, you can really calculate based on the equation, how much of everything else you sort of did. You also can calculate in theory how much you should get out in this reaction. So if you did this reaction, everything worked out correctly, perfectly, this is how much you should kind of get out and produce if everything went perfect in this type of reaction. The units that we use, and we will see pretty much all these units in different chapters along the way. You could do basic stoichiometry type problems like we're going to do here, which usually involves grams and moles. So in a basic stoichiometry sort of problems, they usually involve these two units. And again, as I mentioned, that conversion of grams to moles or moles back to grams using the molar mass from the periodic table as a conversion factor is something that we use a lot here. really in multiple places in these calculations. Sometimes we use it at the beginning of the calculation. We also use it at the end of the calculation as well. So that's very common. When we get into gases, we'll talk about stoichiometry involving gases in that chapter, and we will use something like volume as well as units. It could be any type of unit really, but very commonly grams, moles, and grams are very common sort of units. As I mentioned a second ago, the method that we use is what is referred to as the mole method. And it is literally just that. You're just going to kind of look at the coefficients in the balanced equation, and those are going to give you really a conversion factor. And that's really what stoichiometry is. It's just a conversion factor. Instead of looking up your conversion like in a table, you actually just go through the equation and use the equation as a conversion factor. And really the reason for that is you oftentimes will be given information about somebody in that equation that you're not really interested in terms of the problem, and you need a way to go from the information they gave you to somebody else in that equation that you are interested in, and that's where we kind of get the conversion factor for. These are the general steps that you can follow in a stoichiometry problem, a basic stoichiometry problem. The first step you might not have to a lot of times follow, because a lot of times you will be given the equation, but there could be a situation where you're maybe given just everything in words. And in that situation, again, you want to, as we talked about, make sure that you do get all the correct formulas down first, and then you want to balance the equation. So you always want to do it in that order. Don't try to write the equation and balance at the same time. You want to get just the proper balancing, proper equations like you're doing nomenclature, and then go to the balancing part. Pretty much none of stoichiometry works if you do not have that right there, which is a balanced equation. So everything you would do in terms of a calculation would be incorrect if you don't start with a balanced equation. So that is usually the first step that you start with. Then pretty much whatever they give you, you want to convert them into moles. And once you convert them into moles, that will allow you to use the equation as a conversion factor to go from moles of what they gave you to moles of what you're interested in the problem. And lastly, you'll do some type of conversion from moles to something else. So in a basic stoichiometry problem, there really is kind of 4 steps. Usually you want to balance the equation like we see there. You want to take whatever they give you, convert it to grams, and then grams to moles. By the way, it could be in any unit. It could be like pounds or something like that. But eventually you got to get it to grams and then use the molar mass to go from grams to moles along the way. You then want to go to the equation and get the mole-to-mole relationship. And that's from the coefficients. And then the last step is you should always be in the units of moles at this point when you're doing these steps. You want to convert it to some other unit. And once again, very common is kind of converted from moles back to grams at the end of the calculation. Once again, using the molar mass. Pretty much for basic stoichiometry steps, those are the 4 steps that you should follow. You should always follow these steps in order. And if something is done for you, don't undo it. Just go to the next step. So sometimes people undo and then redo the same calculation. So just kind of go in those steps in that order, and it should lead you to the right answer. So let's talk about an equation like this and really the information that we could get from it. As I mentioned before, this equation is balanced. So what we want to look at in this balanced equation is the coefficients that we see. And we could actually come up with what is referred to as stoichiometric equalities. We could say for every 2 moles of CO that I toss in there, I will also need to toss in there 1 mole of O2. And that is nothing more than the actual coefficients that we see from the balanced equation. I could also say for every 2 moles of CO I toss in there, I will get out 2 moles of CO2. Once again, that is just the coefficients from the balanced equation. I could also say for every 1 mole of O2 that I put in there, I will get out 2 moles of CO2. These are 3 equalities that we could get from the balanced equation. They're sometimes referred to as stoichiometric equalities. They are not equal to each other in terms of 2 does not equal 1, obviously, but they are equal to each other in terms of proportion. that you need to put into that equation to get the product to form. Like if you're making cookies, right, you need so much flour, so much butter, so much chocolate chips to get yourself a dozen cookies that you want to bake. So these are like the proportions of everybody that needs to kind of come together to produce what you're looking for. Now, because these are equalities, these equalities are the same type of equalities that we saw like in chapter 2. For every equality, you could write 2 conversion factors. So for the first one, I could write there are 2 moles of CO over 1 mole of O2, or 1 mole of O2 over 2 moles of CO. For the second one, I could write 2 conversion factors, 2 moles of CO over 2 moles of CO2, or 2 moles of CO2 over 2 moles of CO. And lastly, I could write 1 mole of O2 over 2 moles of CO2, or 2 moles of CO2 over 1 mole of O2. So from this one balanced equation, we actually have available to us 6 different conversion factors that we could use in a problem. And again, like I mentioned before, this is really what stoichiometry is just a conversion factor. And like I said earlier, you're pretty much just going to get it from the balanced equation rather than look up in a table, a conversion for it. Will you use all 6 of these in a problem? I hope not, because you're probably doing something wrong if you are. You're actually just going to pick probably the one that you need. So these are just ones that are available to us to use, and we would pick the one that we need. So for example, let's just say we went through the steps here for a basic problem, and let's just say that we produced in this reaction, we'll go with 15.5 grams of CO2. And we want to know how many grams of O2 did we start with, basically. So our 4 steps that we want to follow. Step number 1 is balance the equation, and that we already did. So we already balanced the equation here. So step number 1 is done. Step number 2 is to take whatever they gave us and convert them into moles. And in this case, we do need to do that because we have 15.5 grams of CO2. Remember, in order to convert to moles, especially when we get it into grams, we need the molar mass. So we would have to go to the periodic table and add up the molar mass of CO2. So CO2 is 1 carbon at 12.01, and it is 2 oxygens at 16. That's going to give us 4401 grams per mole as the molar mass of CO2. That is also really just a conversion factor, right, to convert us between grams to moles. So we'll take our 15.5 grams of CO2. Remember dimensional analysis, so grams are up on top, so on the bottom should go 4401 grams per mole of CO2. The grams are going to cancel, and if we get an answer at this point, which you don't necessarily have to, but we'll get it for right now just to see all the steps, 15.5 divided by 4401. I am not going to round all that much here, so I am going to take it to a few digits. 0.35219 moles of CO2. Actually, I'll write here, CO2. First off, any questions on that step there? That is essentially step number 2. Again, the sort of pathway there is whatever they give you the units in, get them to grams, use the molar mass to convert the grams to moles. Now, the problem is here for step number 3, I am not interested in CO2 ultimately, right? I ultimately want to figure out how much O2. And that is where we need stoichiometry to give us a conversion factor to take us from CO2, which is where we're at right now, to O2. And that is what we could get the stoichiometry to do so. So if we go to the equation like we did, we could see this conversion right here, our equality, that for every 1 mole of O2, I get 2 moles of CO2. And that would give us our 2 conversion factors down here on the right. And The one that we want to use is just like a regular conversion factor. I want to get rid of CO2. So CO2 is on top, right? So that means CO2 needs to be on the bottom to get rid of it. And that's the stoichiometry step. And that's really the third step here. You go to the equation and you find the mole to mole relationship to get rid of what you don't want, which is the CO2 in my case, and keep what you do want, which is the O2 in this case. Once again, here we're going to basically take that number and divide it by 2, and that will get me 0.176, we'll call it 1, moles of O2. And that would be step number 3, which again is the stoichiometry step. So that is the big stoichiometry step. Pretty much just go there and grab the mole to mole relationship from the coefficients and use it as a conversion factor. As you can see, I did not touch the other 2, 4, 5 conversion factors, right? I don't need them. In this case, I just chose the one from the equation that basically works. Is this the answer I'm looking for, though? I'm in units of moles, but I want grams. And that is where the fourth step comes into play. Here we now need to take moles to grams. That means, once again, I do need the molar mass, but I am no longer at CO2, right? I need the molar mass of O2 to do that at this point. So for step number 4, I would go to the periodic table, get the molar mass of O2, which is 2 times 16. Gets me 32 grams per mole. And now I have the last thing that I need. I will take my moles that I just calculated, 0.1761 moles of O2. I will use the molar mass from the periodic table to convert my O2 into grams, moles into grams. So that's a mole of O2 is 32 grams. That is going to get me here approximately 5.64 grams of O2 in this particular case. So what that basically tells me is, if I did this reaction and I produced 15.5 grams of CO2, in order to produce that 15.5 grams of CO2, I had to put in there 5.64 grams of O2. Any questions on that? Again, these are pretty much the same 4 steps, always just repeated, and it should get you there. Balance equation, convert to moles, mole to mole relationship, and moles to some other unit. Any questions on that there? Okay. All right, so that's our conversion factors we talked about. So why don't we try one here? Lithium metal reacts with water to form hydrogen gas and lithium hydroxide. We want to know how many moles of hydrogen can be formed by the complete reaction of 5.32 moles of lithium with water. So hopefully you know this for the exam. Lithium is Li, right? Reacts with water, which I hope you know is H2O. Forms hydrogen gas, right? Hydrogen gas is H2, yes. And lithium hydroxide, LiOH. Lithium is +1, hydroxide is -1. And that is the unbalanced equation. So I'll let you pick it up from that point. Follow those 4 steps. You want to balance the equation, convert to moles, mole to mole relationship from the equation, and moles to some other unit. So when I tell you, just want to follow these 4 steps in this order. So obviously in this case we had words, so like we did at the beginning here, we want to just make sure we got everybody down correct formulas first, not worried about the balancing. At this point we then need to do the balancing, and I believe if you put a 2 there, or maybe a 2 there, and maybe a 2 there, you should be balanced. Otherwise, I'm just putting 2's down, I think. But we got 2 lithiums on each side. We got 4 hydrogens on each side. And we have 2 oxygens on each side. So now we have our balanced equation. Now, the information given to us in this problem is we have 5.32 moles of lithium. So we got 5.32 moles of this one. And we want to know how many moles of H2 would we form. So that is where we want to end up, right? So in this case, number 2 is to convert to moles. Do I need to do that in this case? The answer is it's already done for you, so don't undo it. So we can kind of check that one off. We already have it in moles. The next thing we're going to do is actually the stoichiometry part. So now that we have it in moles, we're going to go to the equation and find the two things we're interested in. You are always interested in whatever they gave you, and clearly you're interested in what you're trying to find. And again, this is where we get our stoichiometry relationship. It is absolutely just a coefficient, so no magic here or anything like that. That coefficient is a 2 in front of lithium, which gives you 2 moles of lithium. And the coefficient in front of H2 is 1 in the balance equation. So that gives us our equality. Once again, that equality will give us two possible conversion factors we could use. Once again, you do not need to use them both. You just want to choose whichever one you need. So now we're ready to kind of do a little bit of a calculation here. So we are given 5.32 moles of lithium. Once again, lithium's up on top and we want to get rid of it. So opposite location will do that for us. So we're going to go conversion factor on the right. 1 mole of H2 gives us 2 moles of lithium. Once again, we're going to multiply the top, divide the bottom. The moles of lithium will cancel. And that's going to get us here 5.32 divided by 2, 2.66 moles of H2. That actually is our answer in this case because that is what we're looking for, right? We're looking for moles. If I wanted grams, I would need to do step number 4. And sometimes you may not have to do step number 4. A lot of times you do, but in this case, we don't actually have to do it because that's where we want to stop. By the way, what this number represents is if you put in there 5.32 moles of lithium, everything went perfect, no side reactions, you weren't a klutz and dropped everything on the floor. What you should get out in terms of H2 is 2.66 moles, which you could convert to grams if you want to know how many grams that would represent. This is also what is sometimes referred to as the theoretical yield. And a yield does need to be a product, yeah? So if you're ever looking for a yield, it has to be a product. And this is what is sometimes referred to as the theoretical yield. It is basically the maximum amount of product that if everything went perfect in this reaction, you should actually produce if you actually started with, for example, that many moles of lithium. Any questions on that? Again, same steps here. Step number 1, balance equation. Convert to moles done for us. Mole to mole relationship. No need for number 4 in this step. Yeah. All right, let's try another one here. We'll do the same equation, same reaction. But in this case, we're looking for how many grams of H2 we would produce if we started with 81.75 grams of lithium. Lithium on the periodic table, 6.941, and hydrogen, 1.008. All right, so again, follow those 4 steps. Balance equation, convert to moles, mole to mole relationship, and moles to some other unit. To look, again, we're just going to follow the same 4 steps. So number 1 was already done for us from the previous problem, so we have a balanced equation. We're given 81.75 grams of lithium in this case, and we are looking for how many grams of H2. So step number 2 is convert to moles, and in this case, we do need to do that since we were given to it in grams. So step number 2 here, we would go to the periodic table. That would give us the molar mass of lithium, 6.941 grams per mole that we could use as a conversion factor to do that. We'll take our 81.75 grams of lithium. Again, opposites are going to cancel here, so grams are on top. So we do need to put the 6.4941 grams on the bottom and the moles of lithium up on top. Remember, we're multiplying and dividing the bottom. So those are going to cancel. And that's going to leave us here, if we get an answer, 81.75 divided by 6.941. And once again, you don't necessarily have to get an answer at this point. You could continue on with the calculation, but I am going to just kind of show the answer here at each step so you can see the different steps. At this point, we have now successfully done step number 2. Step number 3 is where the stoichiometry part comes into play. Once again here, we are given information about lithium, but we are interested in H2, so we need the stoichiometry to do that for us. So from the equation, the coefficient in front of lithium is 2, so 2 moles of lithium gives us, again, just like we did in the previous problem, 1 mole. Yeah, we're interested in H2 in this case. So that's why we went in the equation where the H2 is, yeah. No, no, okay. So that is the coefficients from the equation, 2 and 1. Again, given us our 2 possible conversion factors we could use in this case, and again, it's just the fraction. You could reverse it. 1 mole of H2 up on top and 2 moles of lithium. So at this point, we'll continue on with our number. And again, I'm not rounding very much at all here, so I don't get any sort of rounding error. Lithium is up on top, so we want to get rid of it. We're going to go on the bottom, which means we do want to use a conversion factor over here. And that's going to give us 1 mole of H2, 2 moles of lithium. Once again, multiply the top, divide the bottom. The moles of lithium are going to cancel. And we will end up with now something like 5.8889 moles of H2. That is step number 3 done. In this case, we do need to go to step number 4 because we are not interested in moles. We are interested in grams. So we do have to do that last conversion. By the way, this would be our theoretical yield in moles. But here we are looking for grams. So step number 4, we will once again have to go to the periodic table and get the molar mass of H2 in this case. And H2 would be 2 times 1.008 grams per mole. That's going to give us 2.016 grams per mole as the molar mass of H2. And again, that is going to be used as a conversion factor to convert what we have up here, 5.8889 moles of H2, using that molar mass from the periodic table. Moles need to go on the bottom. Remember, the number always stays with the grams part, so it goes up on top. Moles cancel. We're going to multiply basically here. And if we do that, we end up with 11.87 grams of H2. This, once again, would be our theoretical yield in grams. And this guy here would be our theoretical yield in moles. And it could have it in any type of unit. Once again, hopefully you can see it is just the same 4 steps. As I mentioned before, they actually would prefer you here not get an answer in between each step. So you could definitely go from here to here to here all in one calculation and get the answer at the end. That's actually how they prefer you to do it. I personally don't care if you want to get an answer in between, just don't round too much to the very, very end. By the way, in terms of sig figs at the end there, probably our original number there with 4 significant figures is what we're looking for our answer. Any questions on any of those steps there? All right, let's try one more here. This is the one we just did, so I'll scroll it across in case you want to see it later. All right, so let's try this one here. If you started with 765 grams of C6H12O6, how many grams of CO2 would you produce? So we're looking for grams of CO2 in this case. Let me give you some numbers that might be helpful from the periodic table. So we're looking for grams of CO2, and we're starting with 765 of this guy. Carbon 12.01, hydrogen 1.008, and oxygen 16. All right, so again, follow those same 4 steps, see what you come up with. Okay, let's take a look. So again, even if it may look a little bit more complicated, if it's a basic stoichiometry problem, it really is just these same 4 steps. So in this case, the equation is balanced. Probably if you see coefficient, it is probably balanced. If you don't see any numbers there, you probably should take a hard look at it. You should still probably take a look at it if you do see numbers, but usually it'll probably be balanced. So that's done. Again, we're given 765 grams here of our glucose, and we want to know how many grams of our CO2. So we do need to do number 2 there, which is convert our grams into moles. So we need to go to the molar mass there for C6H12O6. Remember, all we're doing is just adding up the parts from the periodic table. So there are 6 carbons, each at 12.01. There are 12 hydrogens, each at 1.008 from the periodic table. And there are 6 oxygens, each 16 from the periodic table there. That's going to give us here a molar mass of 180.2, looks like, perhaps. About 180.2 grams per mole. Remember, that is really just a conversion factor that's going to allow us to do our conversion we need. So 765 grams C6H12O6. The grams are on top, so we need to put the 180.2 grams on the bottom so everything cancels out correctly. And if I do that, right at this point, I am really in units of moles of C6H12O12 or O6. And that would be step number 2. Like I said before, you could get an answer at this point, but if you know you're going to need to continue on, you could just continue on. And again, setting up with dimensional analysis, as we talked about previously, is really important. I can see the moles of the C6H12O6 are up on top. I need it in the opposite location. But I'm going to do step number 3, which is go to the equation. So I'm interested in this one, and I'm interested in what I'm finding. And I can see from the equation, for every 1 mole of that C6H12O6 I put in there, I get 6 moles of CO2. And again, that is what's going to give me my conversion factors I could use. 1 mole C6H12O6, 6 moles of CO2 are 6 moles of CO2. 1 mole C6H12O6. Once again, if I set it up like this, I can see the C6H12 is on top. So we do want to use the conversion on the right here, which puts it in the opposite location on the bottom. So from the equation, 1 mole of C6H12O6 and 6 moles of CO2. Again, top and bottom are going to cancel, and that's really step number 3 there of our process. If I were to end the calculation right at this point, I would be in moles of CO2, which again is the theoretical yield here in moles, but I'm actually interested in grams. So I do need to do the 4th step, and the 4th step here would be converting our moles of CO2 to grams of CO2. And we will need, again, the molar mass to do that. So back to the periodic table to get that. 12.01 grams per mole for the carbon, 2 times 16 for the oxygen from the periodic table, much like we saw earlier, 4401 grams per mole. That again is going to be our conversion factor here. We could tag on the end. CO2 is on top. That means moles of CO2 need to go on the bottom to cancel. 4401 grams of CO2 up on top. The moles are going to cancel. Once again, we are doing step number 4 there, and we are multiplying everybody on top and dividing, right, by whoever's on the bottom there is essentially what we're doing. And if we do all that, we will have 765 times 6 times 4401 divided by 180.2. That's going to give us something like 1,121 grams of CO2 would be produced, which again would be our theoretical yield. We're looking at sig figs, which we probably should be. That is 3 sig figs. So maybe something like 1,120 grams of CO2 in this case would be appropriate. Once again, hopefully you should be able to see a pattern here. Same 4 steps, just follow the steps step by step. Should lead you to the right answer. In this case, I did not get an answer in between, which is perfectly fine. It's actually how they prefer you to do it here. But if you do want to get an answer, just don't round to the very end along the way. Any questions on basic stoichiometry problems? All right, I think that's a good place to